All right. Yeah, exam is due Wednesday. Okay, so let's get about doing some things. So, let's see. Okay, there we are. Whoops. So, let me just start out with number one. Talk about a few tips and anything. So, this is an interesting problem for a number of reasons. I think it's good because it gets you to think about what this means here. So basically, I'm going to talk about this side only. Figuring out the other side is a little bit more standard. But basically, the hint is this. So if you name three elements, if you have A, B, and C are all elements, then n choose k is the number of ways to pick k from a bag of n items, of which A, B, C are three of them. Okay, so that's the hint, is that you're going to name three elements A, B, C. And now, if you ask what n minus 3 choose k is, well, technically this is just choosing k elements out of a bag of n minus 3 things. But in this case, if we are thinking about our hint at all times, then eventually what we're going to realize is that, oh, this means don't pick, or I should say, yeah, pick k elements, but don't pick A, B, or C. So that's the number of ways to do something on this side, right? So n choose k minus n minus 3 choose k, when you're subtracting this, what you're going to get is the number of ways to pick. Let's think. So this is the number of ways to pick anything, k elements out of n in a bag. This is the number of ways that we're going to only pick elements that are not A, B, and C. That's the terrible way to say it. The right way to say it is this is the number of ways to pick elements that aren't A, B, and C. So there we go. And then, so then what we do is we say, okay, given all that, if we subtract those, then this is the number of ways to pick n thing, or k things out of n, such that we must pick at least one of A, B, or C. Now we don't have to pick all of them, but we do at least have to pick one, because this is the number of ways to pick randomly, and this is the number of ways to pick such that you don't get A, B, or C. So if we subtract that off, then it's the number of ways to pick essentially randomly, except we can't avoid all of them. We have to get at least one, right? Okay, so that's really what I want to say about this. So this is like expanding on this hint. I mean, this is really equivalent, right? This is the same. To say this is to say all of this stuff here, inevitably. Yeah, the video will be available because it's just I'm going to leave the live stream up. So, yeah, don't worry about it. Okay. Let's go to the next page and see what's here. So, oops. No one's asked about number 2, which means number 2 is very easy. And I agree. So maybe I won't spend much time on it. I guess my only hint is probably that you want to think about it as like a is equal to 3x, b is equal to 2y, and consider the term in the binomial expansion of a plus b to the 20th power. But other than that, that's, I mean, I shouldn't have to say this. I didn't say this. Okay, let's move on. Actually, most people haven't asked about number 3 either. So that makes me happy. Yeah, so I guess the one thing to say about part B is this. So part A, my hint is it's simple. It's like a one thing answer. So in this case, how many different ways can you arrange yourself if the couples have to sit together? Yeah. So the answer is 5. No, I'm kidding. The answer is that what you have to do is this is what I'll say. The order of the couples matters. So it matters which couple. So if you have couple 1, if you have couple 1 sitting here, couple 3, couple 6, 2, 5, and then 4, right? So, you know, what kind of thing tells us the number of ways to do this, but then inside of each couple, you have person A and person B, and the other option is person B or person A. So you also have to take the order of couples matters and the order inside a couple matters. Okay. So, what should I say? A bakery sells donuts. So, how many boxes of a dozen donuts can you make out of chocolates, Boston creams, and sprinkles? So, what we're going to assume is that all chocolate, all Boston cream, and all sprinkle are essentially indistinguishable. And what that means is that it suffices to say that I got a box of, say, 4 chocolate, 4 Boston cream, and 4 sprinkles, versus maybe 6 chocolate, 2 Boston cream, and say 4 sprinkles again, or whatever, right? So this suffices as a as 2 different ways to configure a donut box. So my hint on this one is really stars and bars. You know, rewrite this as a linear equation in a certain number of variables, and you know, the sum is going to be 12 because it's a box of a dozen donuts. That's it. So this one isn't so bad. I think most people have been saying pretty happy. Well, I accidentally introduced stars and bars when I picked an example that was too hard, but I think there is a lecture. I don't remember exactly which one it is, but we can find it, where I did a number of stars and bars problems. Okay, so now we want to do the hard one. So this one is interesting, I guess. This one is the fun problem. So Oh, you know what the worst thing that can possibly be told to a teacher um, is when someone says you didn't teach us this. It's the one thing that, well, makes this teacher uniquely angry. Uh, he has a number of emotional reactions to that. So anyway, um, okay, so let's talk about this. I've done at least one example. Um, so let's not do this problem. Let's do a different problem of the same type. So let's say that we want x plus y plus z is equal to 19. And let's say that we want 2 less than or equal to x less than or equal to, I don't know, 16, 3 less than or equal to y less than or equal to 12, and 0 less than or equal to z less than or equal to 5. So, okay. Should we make this a little easier on ourselves? We are going to. So we're going to make this 25,329. So this number is going to be important for a reason. Okay, so how do we compute the number of integer solutions? Well, so the first thing is we dot our e's like this. And then the second thing is we first we have to deal with these lower bounds. So what we can do is we can subtract off 3 from all sides, and then what we get is like 0 is less than or equal to y hat is less than or equal to 9, and that's what happens if we subtract off 3 from both sides. And then for instance 2, if we subtract off 2 from all sides, we'll get 0 is less than or equal to x hat is less than or equal to 25,327, which obviously really is going to matter in this problem. Yeah, I mean, and then here, if you want to hat z, z gets hatted in the same way. So now we have the new equation. We have x hat plus y hat plus z hat, if you're Canadian or British, is equal to 19 minus 3 minus 2, which is equal to, if I'm not mistaken, 14. Okay, so cool. Now, how do we do this problem? Well, oh, perfect. We're going to see an edge case that not even the test problem really deals with. So, okay. So here's our equation. So now what we're going to do, so what are we going to do? So yeah, now what we're going to do is, you know how many total solutions of this there are, right? 14 plus 3 minus 1, choose 3 minus 1, right? Stars and bars. So that's the number of total solutions. But now how many solutions, let me be more specific. This is the number of total solutions where we only have lower bounds. So no upper bounds. So this is specifically all the solutions, even solutions where x is bigger than whatever, y is bigger than 9, z is bigger than 5. So what I need to do is I need to compute the solutions where y is strictly bigger than 9. And the reason why I need to do this is, or I guess y hat is strictly bigger than 9. And the reason why I need to do this is I need to subtract them out of these set of solutions. So what we're going to do is we're going to say, okay, what happens when y is strictly bigger than 9, meaning that y hat is bigger than or equal to 10. So now our new lower bound, so technically we have 2 lower bounds now, but this one stopped mattering. We're going to have this lower bound, which is y hat is bigger than or equal to 10. So what we're going to do is we're going to subtract off, so we're going to get x hat plus, say, y double hat, because we're going to subtract off 10 now from both sides, plus z hat is 14. So now the question is how many, so how many solutions are there now? Oh, I'm sorry. If this is y double hat, we have to subtract off 10. So this is equal to 4 now. So the number of solutions is 4 plus 3 minus 1. So I'm just going to say 4 plus 2, choose 2. Okay. So now we compute the number of solutions. Where x hat is bigger than, no, I'm sorry, z hat is bigger than 5. So that means that z hat is bigger than or equal to 6. So that means what we're going to do is we're going to use the original equation, x hat plus y hat plus z hat equals 14. Well, so the reason for the double hat is because y hat was equal to the original y minus some, it was minus this 3, right? And then y hat is equal to y hat minus 10, right? Because now we have this, we're subtracting off 10 from y, right, to make this 0. So in order to have, in order to prevent us from having y hat minus 10 on this side, we just rewrite it as y hat, or y squared hat. Yeah, I mean, I'm not going to be very sticklerish about the notation of all this. I'm literally, I mean, having a double hat is, I mean, isn't that almost like a joke? I think, you know, definition. So this is x hat plus y joke plus z hat is equal to 4. And so, well, because we've already subtracted, right? Because we've already subtracted off this 2, we've subtracted off this 3. So we've shifted everything down so that everything starts off at 0. But now, yeah, so anyway. Anyway, right, so what we're going to do now is subtract off 6 from both of these. So minus 6, minus 6. So now the equation what we're going to get is x hat plus y hat plus, now it's going to be z joke is equal to 8. So what we're going to end up with now is, what is it, 8 plus 2? Choose 2 solutions of that. Okay. So now we need more space because we're out of space. But I promise you it won't be so bad. I'm going to go up here, actually, because we don't need much. We don't need much room. All we need to do is say that, what if y hat is bigger than 9, so that means y hat is bigger than or equal to 10, and z hat is bigger than or equal to 6. You know, what if? And the answer to that is, well, here's our equation. X hat plus y hat plus z hat is equal to 14. And so what we're going to do is we're going to say, given this equation, we're going to say, well, if we did both of these at the same time and we said x hat plus y hat minus 10 plus z hat minus 6 is equal to 14 minus 10 minus 6. And so what we're going to see here is on this side we're going to get negative 2. And then on this side we're going to get x hat plus y prime plus z prime. You know, I'm just making up new variables. But the whole point about this is that technically what you would be getting here is like a minus 2 plus 2, choose 2. So you'd be getting like a 0, choose 2. And so this is what I'm talking about in terms of the edge case, that even in this exam, you're not actually seeing this edge case particularly, But the point is that out of a set of 0 things, how many ways can you choose 2 of those things? So generally, you're going to have to define things where you have like some negative number. Choose something. You're going to define that as 0. And you can define 0 choose x as... well, I was about to use the Dirac delta function where it's like delta x0, but maybe I should just say what that means. Basically, it's 0 if x is not equal to 0, and it's 1 if x is equal to 0. So 0 choose 0 is 1. But basically 0 choose 5 is just defined to be 0. Ooh. Let's see what we got. Ah, yes. So thinking to buy infinite oil stocks right now since it's negative. Okay. So for the portion, yeah, so if you have a negative in the top, it's just going to be 0. And that's good, right? Because the thing is that what you're going to see here, and so another question that I should have is, you notice that I didn't use this x is going to be bigger than, like what if I did the example where I said, okay, so in this example, so, you know, theoretically you could ask, like, why didn't I do x the same way I did y and z, right? I only made y hats and z hats. I didn't make any x double hats. And the reason why is because if you subtract off 25k from both sides, basically what you have is you have x hat plus y hat plus z hat is equal to negative whatever, right? And the point about the stars and bars method is it only counts the non-negative solutions. And so if you have a non-negative x, a non-negative y, and a non-negative z, that just means that it's bigger than or equal to 0. Each one of them is bigger than or equal to 0. So then the sum of them is bigger than or equal to 0. So it's just impossible to get a negative sum. So the number of solutions to this zero solutions. And so that's a good thing, because then you know that there's not going to be any wonkiness coming out of these terms. So incidentally, well, so, you know, 25,000 is a joke, but do you even need to consider 17, right? So 9, you got to look at. 6, you got to look at. 17, on the other hand, how many donuts can you put in a box, right? If the store has 17 sprinkled donuts, 17 donuts is essentially equal to infinity for you, right? Because you can't tell the difference. If the store has 17 of them and you're only allowed to put 12 in a box, and you're only allowed to get one box, then there's no way that you're ever going to get up to the 17. So it really doesn't matter. If they have a dispenser that dispenses donuts and you ask for 12 sprinkled donuts, you'll never know that there was only 5 of them left. So in this case, that's why I'm saying, like, 17 is as good as 25,000 is as good as infinity. So you don't have to even consider. So basically the point is that if you consider the number of sprinkled donuts, and we say like chocolate donuts plus Boston cream donuts plus sprinkled donuts is equal to 12, right? Then the point is that normally you would say, oh, 0 is less than or equal to s is less than or equal to 17. But then you would look at this upper bound and you would say, we actually will never ever hit this upper bound. So it's okay just not to consider the upper bound at all. And what that means is that, remember that these stars and bars methods only consider unbounded variables, right? And so because it only considers unbounded variables, right, it's bounded below at 0 so that it's non-negative, but in the upper bound it's not bounded. And so that's the point here, is that if it's 17, you can ignore it. Yeah, so if all the numbers were less than 12, let's say that they were all 3. So let's say that, let's say that they were all, let's say that there were 7 chocolates, say that there were 6 Boston cream, and say that there were 8 with sprinkles. So then what you would have to do, unfortunately, is you would have to do, so it would be 12 plus 2, choose 2. This is unrestricted. But then you would have to subtract off 3 different ones for being bigger than each one of these individually. So then you would have to say, well, if I pick at least 8, so bigger than or equal to 8 chocolates, then I have 4 left, so that's a 4 plus 2, choose 2. This is for chocolate. This is for Boston cream. And this is for sprinkle. So for sprinkle, then you would say, okay, this has to be bigger than or equal to 9. So then you would subtract off 9, so you get 3 plus 2, choose 2. This has to be bigger than or equal to 7, so you'll get 5 plus 2, choose 2. So this is one thing, and actually it doesn't add that much, this doesn't add that much to the complication, mainly because the point is that you're going to end up with a bunch of double intersections now, 3 double intersections. The double intersection of, say, chocolate and Boston cream. So if you pick more than, or at least, more than 7 chocolates and more than 6 Boston creams, that means that you're picking at least 8 and 7. So that means you're subtracting off 15. So you'll get a minus 3 plus 2, choose 2, which is negative. And then this will be Boston cream and sprinkle, which is going to give us what? Boston cream and sprinkle is going to give us even more negative. It's going to be, like, this is already negative 1, choose 2. Boston cream and sprinkle is going to give us negative 4 plus 2, choose 2. So that's going to be negative 2, choose 2. And then the other one is going to be this one and that one, which is going to be 1 more than that. So it's going to be minus 5 plus 2, choose 2. And this one's going to be chocolate and sprinkle. Yeah, so for the original problem, you still need to do 2 of them. So, and then of course, let me just say the last part here. Then you have to subtract off the thing where we have all 3 are bigger. So then you would end up with whatever that is. So I guess that's actually minus 24. So it'd be minus 12 plus 2, choose 2. So it'd be minus 10, choose 2. The good news is all of these terms are all 0. These are the non-zero terms. So actually it only adds on 1 extra non-zero term, even in this other case. Well, the thing about the inclusion-exclusion principle is that it's alternating. I think the way to look at it is this way. So let's be very careful about it. So A is going to be the set where, so A is the set where x is bigger than the upper bound for x. And B is going to be the set of solutions where y is bigger than the upper bound for y. And then C is the set of solutions where z is bigger than the upper bound on z. So we're defining all of these sets. And so what's going to end up happening is what we don't actually want A union B union C. Because those are the answers that are all invalid. What we want is A union B union C complement. And so that's kind of the problem here. So the number of total solutions, so like the number of things in the universe that's equal to the original stars and bars. And so what we want to do is we actually want to subtract off. We want to take the number of things in the universe and subtract off the number of things in A union B union C, which is then equal to the universe minus A minus B minus C, and then plus A intersection B plus A intersection C plus B intersection C, and then minus A intersection B intersection C. And so that in total, this equation here is going to be equal to the number of things in A intersection B, oh no, I'm sorry, A union B union C complement. So that's basically the equation that you need, which is why, I mean, essentially, if you have the double union or the triple union, let's just do it with the double union formula. So you have the number of things in A union B is equal to the number of things in A plus the number of things in B minus the number of things in A intersection B. But let's say that you actually wanted to compute it another way. What you would want to do here is you could actually say, well, A union B minus the number of things in A minus the number of things in B is equal to negative, technically negative in A intersection B. So you see how it's not really, and so if you add this to the other side, you can get a plus sign here, but then you get a big 0 sign here. So the inclusion-exclusion principle is stated in terms of alternating things. So if the original sets are positive, you see these are being added, and then the next one is subtracted. Triple union or triple intersections would be added. Quadruple will be subtracted. On the other hand, if you switch everything to the other side of the equation, what you see is that because the sums are alternating, now the singleton sets are subtracted and the union is added. But it's as long as you stick to the convention. So basically this. So if this is basically like the number of things in the universe here minus the number of things in A minus the number of things in B minus the number of things in C, and that's what this is. And then all of the x intersection y's, they're all 0 for x and y in A, B, C. Okay. You know, this is a lot of fun now. This is probably too much on a single thing. Yeah, so if you wanted chocolate more than 9, then you have to start chocolate is greater than or equal to 10. Okay, I've said probably infinitely more than I should have about this problem. Let's move on. Okay, don't click then. All right. Oh, this one. I don't think a single person has said anything about this. Or maybe they have. Ah, yes. Okay, so there have been 1 or 2 people. I think, never mind. So some people have said stuff about it. Well, if you remember back, there is a thing whose definition is the answer to this problem. Right? If I have 8 people and each person has a computer, and I'm going to permute those permute the computers. Yeah, D something. My hint is derangements, right? And that's my hint for all of these parts. You're going to have to use some version of combinations and some version of derangements to attack this problem, because that's what it is. Well, it's, you know, how many ways can 8 people not get their hats back or their computers back or whatever? Well, you know, shouldn't be terribly surprising what the answer is to that. More than half. So this one, you're going to have to add up a bunch of them. But this one is a single a combination or derangement. This one is a single combination or derangement. And actually, I shouldn't say that. This is actually 2. What I meant by a single one is that it's a single term. So it's 2 things multiplied together. It's a single term. Which means that, like, I mean, x squared y is a single term, right? So when 2 things are multiplied together, that's 1 term. And then this will be, I don't know, 4 or 5 terms, more than, so it'll be 4 terms. Okay. Yeah, so I don't want to say too much more about this problem, mainly because actually what I've written here is longer than any of the individual answers for any of the parts, so you know, I really don't care about evaluating numbers like that, and the reason why is because if you say something, especially if you said something like 327 choose 15, right? Now, that is not the answer to anything. But the point is that 327 choose 15 kind of means something. But if you write out a large number like, you know, 528,392,157, also this is probably not equal to, you know, in no way, I just made up this number on the spot. So this doesn't really mean much, right? This is kind of meaningless. And so I tend to like combinatorial terms better than I like just raw numbers, because to me, raw numbers kind of have lost, like, essentially all the meaning has been stripped out from what this number could have meant if it was actually one of these combinatorial terms. Cool. This problem. I think everybody said that this problem was their favorite. I think no one had any problems, right? This was the easiest problem on the exam. So actually, this one, so what I will say about this one is that it's not as hard as you might think. And the reason why it's not as hard as you might think is this. This is the answer, right? And I swear to you, when I was writing this problem down, I was like, man, this is not just going to be enough of a hint. This is too much of a hint. And so, and then I realized, the one thing that I was realizing is that, the one difficulty is that it also uses n and k, so you might think that this n and k are the same as this n and k. So let's fix that. So instead of writing it as n choose k here, let's write it as, okay, no, I was about to do something. My instinct is immediately to do something like, oh, alpha choose beta. But instead of using Greek letters, which I'm sure that most of you are going to feel somewhat put out by, let's just use A choose B. A choose B is equal to A minus 1 choose B plus A minus 1 choose b minus 1. And this is for all ab. Okay? As long as maybe, let's just ab bigger than or equal to 0 or something like that. So now that this is the case, we can look at this formula with a little more objectivity, right? And we're not trying to fit n choose k into this formula. What we're going to do is we're going to assign a is equal to n plus 1 and b is equal to n plus 1. And when we do that, then the first thing we're going to see is that n plus 1. Also, this was the formula that you had to prove on your homework. So n plus 1 choose k plus 1 is now equal to, so it's a minus 1. So a minus 1 is equal to n plus n choose k. Yeah, so here's the thing. We now know this is the case. So this is definitely true. Now, if this is true, we see one thing. We see, look at ye term, right? So the first thing was we see this term. And then we have this on this side. Cool. Nice. But then you have this extra thing. And so what do you do with this extra thing? Well, the answer is throw it back into the formula, break it down again. Then throw it back into the formula and break it down again, and again, and again. So here you rinse and repeat. And I promise you it'll work out. So yeah, I mean, this problem, this thing here, right? Use this fact. Basically, the entire proof here is this fact. Just what? N plus 1 times? So yeah, figure it out, write it down. This is definitely, if you want to call this a hint, this is like a hint squared. Okay. So yeah, as many of you pointed out, this is B intersection C. So I made all my typos on this page, I guess. We need to fix this one. Let's make this 0.12. I'm going to re-release another PDF of the test. Maybe I'll just fix it up right after class. So draw a Venn diagram. You know what? I think you guys all said this was easy. So I'll let you guys do this one. I don't want to spoil the fun. What don't you like about number 6 then? So you say you're confused. What are you confused about? As I always say, ask me a question or tell me a lie. Oh, what do you do with C? What do you do with this term? Yeah, so you apply the hint again, right? So you need to apply this hint n plus 1 times. So what you need to do is you need to say something like, well, now, if a is equal to n, b is equal to k plus 1, then n choose k plus 1 is equal to, n minus 1 choose k plus 1 plus n minus 1 oops, keep doing that, n minus 1, choose k. And then the same thing, right? So then you end up with this term where you have a, well, I don't even want to do it. I just want you to do it. But that's the point, is that, yeah, so this term is now, instead of being n choose k plus 1, it's n minus 1 choose k plus 1. Well, what is this term? What is this term, right? And then do it again and again and again until you can't do it anymore. Yeah, so the only thing I want to say on this page is I need to fix this, and here's the fix. I will send out another PDF tonight with a correction. But other than that, these problems are just, this is the triple union stuff, and this is the double union formula for probabilities. I mean, I don't even think I'm giving anything away by saying that. So, okay. What else is next? Oh, this one. Yay. This is my personal favorite. I really am. I'm appreciating this problem more and more. So, no, you guys, no, it's no. So, here's the thing, right? I'm gonna let you guys figure out the derivative of this thing. It's technically, theoretically, right? Technically. Theoretically. You've had Calc 1. This is Calc 1. If it's so great, how can it be solved? That's a deep question. Well, the prereq here is Calc 1, so I'm going to just tell you a fact. The derivative of this series here. Now, of course, if you're afraid of this, there's a reason to be afraid. And there are actually some questions of convergence. Because sometimes you may have a certain point in the sequence when the original sequence exists, but the derivative doesn't exist. For instance, well, let's not even... Actually, I think the derivative doesn't exist at the same points, but anyway, you don't have to worry about that. So you can just say that this is equal to the sum of the derivative. And now this one here. So what I'm saying, Alex, what I'm saying is that you don't have to worry about questions of convergence, right? These questions exist if you're in Calculus 2. I don't care. We're going to assume that this thing converges, and we're just going to pass this derivative. So you notice that x and k are not the same variable, right? So if I tell you something, if you remember the thing where it says like the derivative of, say, f of x plus g of x, right? And you would say, oh, well, that's just the derivative of f of x plus the derivative of g. And now, you might say like, oh, well, that's true most of the time, blah, blah, blah. If the derivatives both exist. Again, we're assuming all of that. And so what we're doing right now is then, instead of that, we're saying it's the derivative of f0 plus f1 plus f2 plus dot 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 is equal to the derivative of f0 plus, for some reason the pen is rebelling more than usual right now. Right. So, okay, cool. Well, this is just in case anyone was afraid of this part of the problem here. So the nice thing is we get a nice formula for the sum of kx to the k minus 1 power. And this is just, it's great. So now if we want to, so I've used up way too much space on this thing. So now we're going to use the identity to find the expected value of the probability distribution given. So, so remember what the expected value is, right? So first we're going to remember the probability that x equals k for the binomial distribution. The definition of this is n choose k, p to the k, 1 minus p to the n minus k. So that's the definition. Yeah, this is only b. I didn't do a yet. And so the expected value of any probability distribution is the sum over all the sample space elements that the probability of x is equal to s times s itself. Now we're assuming that s, all the values in the sample space, are in some kind of let's just say some kind of field where it can either be, or I guess really I should just say a ring. So it can either be the real numbers, the integers, the rational numbers, the, I don't know, the natural, anything. So technically it could even be, you could have a complex expected value if you were brave enough. It just has to be something that can be added, right? The plus sign, basically s plus has to make sense. If s plus doesn't make sense, then we have, oh, I'm sorry, not plus. Well, no, plus and times. So we have to have s plus and times because we need times for the probabilities. So yeah, it has to be a ring of some sort. Anyway. Okay. So this is the definition of the binomial distribution. So now what we're going to do is we're going to sum what we're going to do is sum of from k equals 0 to infinity. Let me just answer a question that someone asked me on okay. Cool. Actually, you can send the announcement. Well, maybe I'll just wait. Okay. So this is the expected value. So as it turns out, what should I even say about it? So oh, interesting. Oh yes, okay. Wait, what did I ask you to prove? Oh, find the expected value. So, Okay, here's my new hint. And maybe I'll even add this to the PDF, because this is definitely a new hint. The new hint is that k choose n, k times n choose k is equal to n times, and I'll have to check myself on this. I think this is right. Actually, I'm not sure if the derivative has anything to do with it. Though I was pretty sure I figured that out. Oh, wait a second. Did I change this to binomial distribution? Oh, that's the binomial distribution. I'm doing the totally wrong expected value. Oh, wonderful. Oh, man. Okay. Okay, I was very confused for a second. I was like, what am I doing? Okay. You should be worried, Ben. I think it's 1 minus alpha divided by alpha to the k plus 1. Yes, this is the new probability. I was doing binomial distribution. No one told me that I was doing the wrong probability distribution. What the heck was I even doing? So the expected value was equal to sum, k equals 0 to infinity, of k times 1 minus alpha over alpha to the k plus 1. I was seriously about to find the no one understood the problem anyway, so we couldn't. That's a good point. If I'm saying equally incomprehensible things regardless, then yeah, that's a bad sign. 8+ hours is not healthy to spend on 10 problems. Yeah, because you need to spend 12 hours. 12 hours is the amount of time it takes to do a take-home math test. It's just a simple fact of life. So you still have 4 more hours to go. Anyway, let's talk about what things we can do to this sum. So, basically, I'm going to give you some hints, and these hints are going to essentially solve the problem for you. Remember that 1 minus alpha is, what should we call it? A constant. Yes, that is true. It is very constant. The only thing that's not constant here is k. So we're allowed to pull out the 1 minus alpha, and now we have a better looking formula. That's true, and the sunk cost fallacy is also real, so you want to be careful. But you see that this, right, this is like 80%. This is 80% with the formula, right? We only have one thing that's different, right? So if this constant we can ignore for now, the only thing that's different is this +1, right? In the formula, we're going to get the sum of kx to the k minus 1 power. Here we have k plus 1. Well, the good news is that alpha to the k plus 1 is equal to alpha squared times alpha to the k minus 1, like that. So yes, if you were doing the binomial distribution, you have to do something completely different. But for this one, my hint, thank God, was exactly the right hint. The reason why it was the right hint is because it was the hint that I came up with when I solved the problem. So here we have this. so this is the second hint. And so if you do this, then you're going to end up with 1 minus alpha times, let's see, I think you factor out an alpha squared for the denominator, divided by alpha squared, times the sum of k equals 0 to infinity of k, and then 1 over alpha to the k minus 1 power. And so then this is the hint from part A. And this is just something. Interesting. I was just thinking what the yes. Okay. Yeah, so as it turns out, when you're doing this problem, as it turns out, if I actually decided to have done the real problem, then this hint really helps. Well, as I say, how do you take the derivative of sum? Well, what you do is you just shove the derivative sign inside of the sum, and you take the derivative term by term. The derivative gives a completely different value, so how could that work here? What do you mean a completely different value? So, I mean, that's the thing. Like, if it's like a sum of number, well, I guess even then it's the same, right? So if you have a sum, say from k equals 1 to 5 of f sub I of x, and you're taking the derivative, this is the same thing as taking the derivative of f1 plus f2 plus f3 plus f4 plus f5. No integrals. I mean, it's good that you know that so the thing is that we're going to generate a new formula, right? We're taking the derivative of both sides of the equation. And when we take the derivative of the second side of the equation, that gives us this term here. So this part A term. And then the answer to this sum is the other side of the derivative. And so given that you want that other side, you don't want to take an integral to get it back. Yeah. Anyway, so for finite sums, there's no problem with this for finite sums. The real problem is when you take the limit as n goes to infinity and replace 5 with n. The question is, does this remain true? And the answer is sometimes. Well, yeah, as I'm saying, technically none of this is Calc 2. Because you don't have to, so all of the things that you learned in Calc 2 have to do with convergence and have to do with the worries about exactly what, well, I mean, so, I mean, in my defense, taking the derivative, this is like the, of 1 over 1 minus x is the hardest derivative you have to take. And, I mean, this is a take-home exam, right? Yeah, so there's a website called Wolfram Alpha. So what you do is you take okay, if the thing ever actually finishes. Wonderful. It's embarrassing me. How dare you? I could have actually taken the derivative faster than you. Come on. Wow. Okay, never mind. Don't use Wolfram Alpha. Wow. You are an embarrassing pile of crap, Wolfram Alpha. How dare you? I literally could have just... So what Wolfram Alpha would have told you... let's see. Is there an alternate? I don't know. What should I say? Oh, geometric series. Okay, cool. Let's see. Geometric series. So here it is. Here it is. Let's see. Do they talk about the... So here it is. Yeah, so you can differentiate the geometric series. And this is, this is where it is. Now, of course, I mean, I don't expect you to know that you should search geometric series because almost certainly the article will have had the derivative in it. And, that's just something that I kind of imagined because Wolfram Alpha is now Wolfram Delta. They have been demoted. Well, if this ever starts working again, then you can use it. But otherwise, you can just go into the geometric series site, and you can pretend like you solved it. So really, what I want you to do here is I want you to show me the work for how you get both of these derivatives, the 1 over 1 minus x squared and the n x to the n minus 1 business. That's really it. Okay. Well, I mean, we didn't cover derivatives. I'm not doing any reviews on derivatives. The reason why I included calculus is because it is a prereq for this course, and I figured that this is not the worst problem. You can join me now, Ben, if you really want to. You want to come in? We're almost done. Well, I mean, if you just use Wolfram Alpha, then you certainly have to show work. This is a math test. What's extra credit? I don't even understand. Okay. Well, then it's a perfect time. Okay, and then this one is... So this one is straight up binomial distribution. And I don't want to cover it. Have you now? Oh, I see. Okay, let me make you more audible. You're not even audible to me. Hello? Oh, there you are.
Hello? Oh.
I've turned you on.
Oh, I should mute the stream.
Yes, you should.
Can I hear you? Why can't I hear you here? No. Uh-oh. Sorry. Keep, I'll be, Oh, wait, I think I could fix. Okay. Sorry about that.
Wow.
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 Wow. We're here.
You're amazing.
Oh, you are too.
I know.
So is this the test they have in flight now, and you're giving them some helpy hinty hints?
Yeah. They wanted hints.
That's
and
good.
And I'm like, the world is ending.
Yeah.
Coronavirus will probably kill us all within a week. So,
Maybe
hey.
it's a little alarmist, I think.
Anyway. So, how many times must we fire an arrow to guarantee that we have 99% chance that we at least hit the target once? So,
Oh,
this is a fun problem.
yeah.
Oh, you know me. So someone just said thanks for the pessimism, and you see, Ben J1 understands the fundamental nature of my pessimism. It's been cultured over the past, 20 to 30 years.
I feel like every time I join your stream in progress, you're blasting womp rats in a problem.
Yeah.
Also, why didn't you write this as blasting womp rats?
All right, I'm gonna rewrite it. I told them I'm gonna release a new one. So, what's Biggs, right? Has a 25% chance of scoring a target on a Womp Rat.
That sounds
In
right. Biggs
in
probably isn't a very good shot. He's a supporting character.
in Beggar's Cannon, he'll shoot 32 blaster shots.
Mm-hmm.
Problem fixed.
Mm-hmm.
Right? I mean, I think honestly, this is. I think we've improved the problem.
Now we're having fun.
So, yeah, I mean,
Or like I said, you could make this. You kill a monster in World of Warcraft, and it has a 25% drop rate.
no, we're not doing that problem yet. Later.
No, this is a simpler version. How many times you have to kill the monster to get your item, or to have
Oh,
a 99% chance of getting your
yeah. I
item?
mean,
Same thing. Same thing.
yeah, not yeah.
Yeah,
Okay,
no, yeah. What are you, Australian?
okay. So, if we remember, the only number that we really need is that the probability of success is 0.25%, or 0.25, or 25%. And so if you guys remember, this is the really cool little 1 minus trick. So basically what you want to compute is the probability of never hitting the target. And the probability of never hitting the target is equal to, it's equal to always missing, so you have a 75% chance of missing, to the power of the number of times that we shoot at the Womp Rat in Beggar's Canyon. Now remember that there's technically an n choose 0 here for the number of successes, and technically there's also a 0.25 to the power of n minus n, if you're a big believer in the binomial distribution, which I am. But remember that 0.25 to the 0 power is just equal to 1, and n choose 0 is equal to 1. So we can just drop these terms. Whoa, that's not even a thing. So this is our magic quantity, right? But almost, right? Because we don't want the probability of never. Well, we do kind of. If we want a 99% chance that we're going to hit the thing, then we want this thing, this 0.75 to the n, to be less than 1%. Let me just, we'll do it that way. I was debating.
Joshua Bush is rejecting the theory of binomial distribution.
Well, you see, it's very
welcome it into his heart.
Yes, the fool has said in his heart that there is no binomial distribution.
I wouldn't call Josh a fool.
I'm not saying it. It's Jesus, man. So
no, he's pre-enlightened. He's about to be enlightened. That's where he's at.
You know that quote from Romans, right?
All right, let's not get too sidelined.
Well, no, I mean, two things, Ben. One, I allowed you to come into the stream.
Oh, so you're ready to be sidelined.
Two, hint complete.
Yeah, this is pretty strong hint.
3, I was very wrong. Jesus didn't say it. If it's in Romans, that would be Paul.
Mm-hmm.
And 4, the class is over.
It is over.
So, what do you want from me?
Nothing.
Exactly.
All I want from you is you. That sounds like
Oh
that
man.
sounds like a song.
No, it's all I want for Christmas is you.
No,
That's a
all I want
song. That's a
from
song,
you. That
right?
that is a song, but it's not Christmas time. Is it? Is it Christmas time? Is it?
I mean, it could be. I haven't been outside in 14 years.
Some say that's an exaggeration, but he has a tunnel from his house to campus. Oh,
I'm not sure what the sun looks like.
yeah, yeah. It's big, but far away, so it doesn't look very big from here.
Does it look like a sphere? Or is it still like projected down onto a two-dimensional thing so it looks more like a circle?
Uh, I don't know. That seems like another
Yeah, I mean,
fun thing for people to challenge scientists on.
yeah, I mean, really, when you have a sphere
If the Earth can be flat, why
and
is the sun flat?
we have our plane of existence and we have a projection map, which of course is denoted pi. And here's us.
That's us. We're so far away from each other. We're like 75% of a sun's diameter away from
We're 6 feet. We're properly socially distant.
Okay.
I'm not spreading any of my germs to you.
That's
so
true. Not like the huge. Oh yeah, that's my dog playing in the background. I didn't know that was audible.
It is audible.
When he plays, he sounds like he's being murdered.
Incidentally, guys, the class has technically ended. So I mean, I know that there are still probabilities on the screen, as if that matters. But you are quite all right to just leave the except all of this into your heart.
What do you ever do any like bonus math at the end?
I will now.
Oh.
Let's see. What's a cool problem? Or what's a cool thing?
What's a cool thing?
Oh, you know what I eventually wanted to get to in this class? I wanted to talk about like regular limit regular limit cardinals and stuff like that, and like the proofs involving ZFC. But then I realized, I was like, wow, maybe you shouldn't do that in like the first set theory class, because that could be extremely painful. So anyway, I decided not to do it. But
have you done Big O yet?
No, I haven't touched Big O.
Prep these babies.
Nah, Big O's technical.
Prep the babies.
Big O is technical and boring.
It is, but it's practical.
No, but we're not doing it in an after-school special. So.
Oh, you mean for fun times?
No, yeah, no. What's cool math? You know.
Mm-hmm.
I was thinking maybe
math about birds. Do you have any bird math?
So maybe countability.
For birds?
No.
Oh. You know, starlings murmurate. It's a verb for how they flock.
Uh-huh. Mm-hmm. Well, what kind of...
There's got to be a way of modeling that. It's probably like a wave or something. Like... Countability? Countability
of countability
a man's face with half a mustache?
No, it's a Q.
Oh. Man, now there's dogs barking outside. Bird fetish. It's not. Gosh, you guys are so explicit.
So
I like animals.
So how much do you know, Ben, about countable versus uncountable infinites?
I know that the integers are countably infinite, and that.
Wait, you almost said that they were countably intimate, which I.
That's your smooth jazz album.
So, do you know the definition of countability?
1 second. I'm being summoned.
Lord. I don't know what's wrong with him. Running away when I ask for a definition. Anyway.
Wait, what happened? Okay,
Yeah,
countably
so
intimate. Your jazz on.
countability of either Zahlen or maybe the Q thing, rational numbers. Um, so oh, so
Isn't it have something to do with if something's countable, then you
uh-huh.
can take two elements out of the set, and
Nah,
there's a
nah.
point at. Oh,
Keep going
okay.
though.
Well, okay. It's
Say it.
basically that if you have two things in that well, now I feel like set is a trigger word for
No,
the
no, no.
stuff.
It's
But
it's it. No, set is correct. It's the two things that has me confused.
I thought it had something to do with the fact that like if you have there's like you can't get two values that are like consecutive in uncountably infinite because
So that's
there's always more stuff in between. If you take any pair of things, there's
what
always
you're
more
talking
stuff
about is
in between.
density.
Oh, I didn't know that.
Yeah,
Okay.
so the rationals are dense because between any two rationals,
Yeah.
for all x less than y, there exists a z such that x is less than z is less than y. Ah. So basically, for any two rational numbers that aren't equal, you can stick one in the middle.
Mm.
That also applies to real numbers. You know? Anyway,
Mm-hmm.
okay, so countability, it's actually pretty simple. All that it says is that there exists a bijection with the natural numbers. So it just says that the natural numbers can pump into your set, and it's 1-to-1, and it's onto, which means that each natural number gets assigned to a unique number in the set, and every element of the set is mapped by some natural number. That's really all it means.
Oh, so the natural numbers are countable just by definition.
Well, almost by definition.
Almost.
Technically, well, I mean, if we're being set theorists and extremely pedantic, then what you have to say is that the identity map from the natural numbers to the natural numbers is itself a bijection, which then proves the counter. Did you just groan at me?
No, I sighed because I'm withering and.
but
Ah,
but don't you see that this is technically necessary? If you're a set theorist,
yeah,
you would have to say this, right? You'd have to be like,
you have
well,
to be
the
precise.
identity map, because it's not saying that being the natural numbers is the definition of countability. The definition of countability is that you're in bijection with the natural numbers. So, in order to establish countability, you have to establish a preferred bijection. I figured that would make you laugh.
It's not the fact so much as the presentation, but sure.
Well, I mean, yeah. So, the integers are there's a bijection from the natural numbers to the integers.
Sure.
And what is that bijection? Ben J1.
Uh,
I'll call it the Ben morphism.
I don't know. I'm gonna get this wrong.
It's cool though. So we can actually write it out pretty explicitly. You can
Okay.
just say Ben of x is equal to it's going to be equal to x actually x divided by 2 if x is even.
Oh my God, this was almost what I was gonna suggest. I knew there was some kind of doubling or something like that
Mhm.
because there's twice as many integers. Well, there's twice as many integers as there are natural numbers, with the
Let's
exception of
see.
0.
Yeah, so I think x plus 1 will do it. Yeah, okay. So this is the cool part, right? So you look at what the Ben morphism does.
Mm-hmm.
So Ben of 0. Whoops.
I had to have mine removed, but they
Mm.
still call me Ben. But my Ben morphism is removed.
So it's even, so b of 0 is 0. But then the question is, what is b of 1? Well, b of 1 is odd. So 1 plus 1 is 2. Divided by 2 is 1. Negative 1. b of 2 is equal to 2 over 2, which is 1. b of 3 equals, it's odd, so you add 1, put a minus sign on it. So now what we see is we're going to get 0, negative 1, 1, negative 2, 2, negative 3, 3, all the way up to, infinity and minus infinity at the same time, right? So is this function one-to-one, which just means are there any two objects like n and m that map to the same value? The answer is no. And is it surjective, meaning does it hit every element of the integers? Well, yeah, because pick a number and then just figure out what it has to be. If it's an even number, if you want it to be positive, just multiply it by 2. So if you want a positive number, you just take 2 times that positive number. And if you want a negative number, then you just take 2 times the absolute value of that number minus something like that, right? Something like that. So that's basically the idea. And then maybe like subtract 1. Yeah, that's it. So you see that's it's a surjective map as well. So cool, right? So the integers are countable. So the rational numbers are countable.
I'm still don't see how what this has to do with birds.
Well, you see, you have explained to me that in life, sometimes the number of birds is in bijection with the rational numbers. And so an important mathematical question is, can we count birds or not? Are birds countable? Because if birds are uncountable, then we need to do some integral over some kind of measure space of birds, where right to of a metric, and that it's more complicated if you have to do continuous mathematics. But if it's countable, then there's possibility that we can do some kind of summation or something like that. So yeah, I see. And so basically the cool idea of the countability of the rationals is this: you write down a bunch of dots like this, like so. And so this one, I'm not going to write out the morphism explicitly. I should just say function. I mean, I'm not a category theorist, am I?
You are a funkatron. Wait, what is it? I can never remember what you call yourself. You're like a... Hold on.
Fully faithful functor.
No. No.
And then we number them. I think this is fine. Yeah, 0.
It's proof by picture.
Yeah, it is a proof. It is a picture proof. Well, let me get rid of 0.
It's a proof
just for now. I think I want to make this like 1, 2. I just want to make sure that I don't accidentally introduce any 0 divisors.
Yeah, you don't want to do that. That breaks the universe of doing.
Yeah. Oh wait, I don't know why I did that. It is too low. Here we go.
Oh.
So this is how you do it. Basically, you say, here's the morphism. You start at here, which is like, I guess, 0 divided by 1. And then you continue. This is now going to be 0 divided by 2. And then you move to here. 1 divided by 2. Move to here. This will be, let's see, 2 divided by 2, which is 1. And then you move to here. And what you'll end up seeing is if you do this weird pattern, or not really weird pattern, it's a diagonal pattern, where you just keep going like this, you will eventually hit any number that you want, any positive rational.
Yeah, when do I get a turn? You're hogging it.
All right. Your turn.
Oh, but I don't have a drawly.
So what you need to do...
Game. How do I win?
You need to tell me what is Cantor's diagonalization argument for the uncountability of the reals.
I think it has something to do with Hawaiian Punch.
You know what? It might.
It's gonna punch you. I'm gonna pat the
Wow.
cat's butt. All right, well, I think I have to go eat dinner, but I'm so
Oh,
glad
do
I could
you?
come join you.
Well, you know what the
Yeah, I
good news
do.
is? The
Yeah.
good news is we were actually able to finish the countability of naturals, integers, and I mean sort of kind of rationals. Though this is all you usually ever say about it. Even in like an analysis class, you'll just be like, "Oh yeah, draw this pretty picture," and you're done. And you're like, "Does that really work?" And people say, "Yeah, trust me."
How much of math is coming up with fancy definitions and then seeing how many places you can apply them? Is that all of it? Is there a part where you get like
Well,
uh
my criticism of modern mathematics is that too much of it is actually that.
uh-huh,
So you're not wrong.
cool.
Yeah.
That's
Well,
that's
because I mean,
scary.
like, people invent an object, and they're like, well, what if I invent the more complicated version of that object that we even understand less about?
Mhm.
And the answer is, well, you can do that, but then you understand less about it. I don't know.
Yeah.
So wasn't
All right,
that
well, I'm gonna
fun?
go. It was great. I'm gonna go eat dinner, and then maybe at some point we'll go,
Yeah, a 24
tactically
hour
take over
lecture.
the galaxy.
Just imagine if I lectured for 24 hours. Well, what would end up happening is I would start getting, like, punch drunk, and then I would get almost so tired I wouldn't be able to understand anything. And then I would just fall asleep.
I think you could pull a 24-hour lecture.
Not anymore. I'm getting old, man. It's hard for me
Yeah,
now.
we're old. We're old.
I know.
We're old.
It hits me more than it used to.
Mhm. All right. Well, I wish you all a good night. Go have your dinners.
Yeah, exactly. I'm glad that we
Yeah.
kept so, like, literally about half of the people stayed around for this. What does that
For the
say about
nonsense.
what does that say about
Or
us
not.
or them
Uh,
or maybe us, but probably them? And I'm gonna blame.
yeah, let's blame them. I don't. They just want the highest level math. They're tired of you babying them. They're
Okay,
like, come on, we can take it. Give me
cool.
your conjective, surjective. How did surjective get his knighthood?
He killed the Onto dragon.
Oh, that's scary. I'm glad he did that.
Yeah, I mean, what's that guy? Uh, it's like that Saint George or something who supposedly killed the last dragon. Am I right?
Well, yeah, it was probably St. George.
Well, I mean, you're just
That or
agreeing to agree. You're very agreeable.
that, that or St. George could also be the patron saint of like really big belly burps. It's or he killed the last dragon. It's kind of hard to say.
Here we are. Yes, Saint George died 303, so his name was probably not George.
No, it's probably George. Come on.
Whose name was George in 303?
Language never changes.
Oh.
That's what I've learned.
Also, I've kept you from your dinner for like an additional 5 minutes. You know that, right?
All right, I'm leaving. I'm leaving. Next time. Next time on. What are you doing? What are we doing next time on Wednesday?
I think I might actually do Bayes' theorem.
Oh, that's a good one. That's
Yeah, I mean,
classic.
it's.
I actually know that one.
I mean, but is Bayes' theorem even really a theorem, or is it just so obvious that it's like, well, if it was false, then the universe would just stop existing?
All right, I'll see you Wednesday.
Boom. All right, guys. Chill out until Wednesday, and by chill out, I mean get your exams done. Hopefully, all of these hints have helped. And the last 15 minutes probably hasn't helped anything, but who cares? You don't have to watch it. All right. Later.